Hi, in this lecture, we'll talk about the different forms of writing the Navier-Stokes equations, as well as the pressure Poisson equation and the vorticity equation. So in vector non-dimensional form, this is our Navier-Stokes equation, assuming incompressible flow for Newtonian fluid. And if you look at this equation, you can see that the high Reynolds number case also creates something like boundary layers and creates similar challenges to high-Peclet transport problems that we need to numerically deal with. Now, we can write the Navier-Stokes equations in different forms, which is going to affect how we numerically go about designing schemes for solving those equations. So the most common form, especially in finite element formulations, is the stress divergence form, where we write the Navier-Stokes equation similar to Cauchy's equation of motion. So the right-hand side is divergence of sigma. The left-hand side is the acceleration, including nonlinear convective acceleration. So we talked about this in the Stokes lecture. And then assuming Newtonian fluid, we can plug in this constitutive equation for stress, and we can simplify the equation. So now this form of the equations, writing the equation like this and working on it to derive the weak form, similar to how we did for the Stokes equation, is going to give us traction and physical forces, so sigma dot n, appearing as a Newman boundary condition on our boundary integral terms when we derive the weak form. We can also use other forms of Navier-Stokes equations. One choice is the divergence curve form, where essentially in this case, instead of the Laplacian of u, in the right-hand side of Navier-Stokes equations, this is when we plug in for sigma, you get divergence of sigma is minus grad p plus mu, which is viscosity, times Laplacian of u. So you can take Laplacian of u and replace it with this vector identity, where you have gradient of divergence of u minus curl of velocity. And curl of velocity is vorticity. So this term is simply curl of vorticity. Okay. So now in this form, you have essentially integrated the divergence operator as well as the curl operator into the Laplace, in place of the Laplacian operator for your diffusion, viscous diffusion term. So the case where when we have incompressible flows, this divergence term is zero, and we simply get this curl form where the left-hand side of the Navier-Stokes is the same. The right-hand side, we have minus grad p, and then we also have minus viscosity times curl of vorticity. So this shows you a link between vorticity and viscous diffusion processes, basically. Now, another form we can write in Navier-Stokes equation is the so-called rotational form, where we now use a vector identity to change the nonlinear convective term, u dot grad u, okay, where we get these terms appearing. One of them being the dynamic, something like that looks like a dynamic pressure. If you insert this into the Navier-Stokes equations, what we get is that this form momentum equation, we will not have u dot grad u anymore, but now we have the cross product between the vorticity vector and the velocity vector. And on the right-hand side, we have the curl of vorticity. So essentially, in this derivation, we use this curl form up here. So the right-hand side is already written in terms of vorticity. And then for the pressure, we now get a new pressure that we call total pressure, which is our old pressure plus this dynamic pressure added up. So now this form is interesting because it has it shows you the link between vorticity and velocity in the nonlinear phenomena in fluid flow. It can show you, how vorticity is appearing here. And also, perhaps from a numerical point of view, the interesting feature is that if the flow is irrotational, you have zero vorticity, then for this formulation, the nonlinear term, the advection term, essentially, if you use this formulation, the nonlinear advection term basically vanishes. And its effect is kind of absorbed into this new modified total pressure. Okay, now we will not be using these forms. We'll use the standard stress divergence form. But if you're interested in learning more about these different forms of the Navier-Stokes equation, particularly in the context of finite element formulation and how do they show up in finite elements, I strongly encourage you to look at the textbook by Gresham, which was one of the references I listed in the first lecture. Okay, now let's derive the pressure Poisson equation together, which we'll be using later when we solve the Navier-Stokes equation using fractional steps method. So the pressure Poisson equation is an equation where we take the Navier-Stokes equations, we take the divergence of the equation from both sides, and we use the divergence-free condition to derive an equation for pressure in terms of velocity, an elliptic PDE for pressure in terms of velocity. And that equation, which is known as the pressure Poisson equation, allows us to find pressure using solving this Poisson equation, assuming we know velocity. Now, this is also a scalar equation because we're taking the momentum equation, which is a vector equation. It's F equals ma. You're taking divergence of a vector equation, and divergence of a vector gives you a scalar. So this is a scalar equation. Now, this is the form. You take divergence of the Navier-Stokes, the momentum equation, divergence of gradient becomes Laplacian, and then you have divergence of every other term, which you can actually simplify. Divergence of the unsteady term, if you switch the role of partial and divergence, you can see that value is 0 for incompressible flow. You can also use the same vector identity we used before for Laplacian of u to show that the divergence of Laplacian, assuming again incompressible flow, becomes 0 because this is nothing but divergence of curve. So this highlighted equation is the final form of the pressure Poisson equation. We have Laplacian of P tilde, which is just pressure divided by density, equals divergence of your gravity vector minus your convective acceleration u dot grad u. So if you know your velocity, this becomes a source term, and you can solve for pressure using this pressure Poisson equation, which you will see where this becomes used later in the course. So the equation, you can use this equation. Actually, the interesting thing numerically is that if you use this equation and enforce it, you're kind of indirectly enforcing incompressibility. So if you make sure that pressure is obtained such that this equation is satisfied, you're ensuring that divergence-free condition is satisfied. And this is actually a little bit more natural, perhaps, compared to the coupled UP method we talked about before. Because in the coupled UP method we talked for the Stokes, pressure didn't appear in the incompressibility condition, and that can cause numerical challenges. But here, you're solving for pressure using an equation that guarantees the incompressibility condition. So that kind of like puts pressure back into its role of enforcing incompressibility. And this equation is elliptic, which means that if my velocity field changes at a time step, pressure will instantly respond, right? So everywhere in the flow, constantly pressure will adapt and will change such that the velocity is always divergence free. Okay, so there's no time delay for that. So pressure instantaneously adjusts itself everywhere to ensure that at all times the velocity field is incompressible. That's the property of an elliptic equation, and it makes sense based on our understanding of incompressible flows, where you have infinite propagation of just wave speeds. You don't have compressibility or pressure waves, right? Things like information is instantaneously propagated. So the alternative to this is the UP formulation, which we already saw for the Stokes equation. That causes some challenges, and we're going to also talk about that later in the context of Navier-Stokes. Now, one thing is that there's also another form of the pressure Poisson equation known as the consistent pressure Poisson equation, where we do not ignore this divergence of Laplacian. So even though mathematically we can easily prove that divergence of Laplacian of u is 0, in practice, second derivatives are tricky to numerically deal with, right? So, in practice, it might not be really numerically exactly 0 based on our data or numerical calculations. So it practice, shows that it's actually better to keep that Laplacian of u term. Even though we know its divergence is 0, it's better to keep it because it gives us better, numerically it has better properties and it leads to better results. So this is known as a consistent pressure Poisson equation. Okay. Finally, we also have the vorticity transport equation, which we'll not be using in this class, but I'll just mention it briefly. So if we take the momentum equation, if you take the curl of both sides, we can derive this vorticity transport equation. So this is a derivation you all see in your graduate level fluid mechanics class. So you get this vorticity equation. So what that means is that you can, if you look at the vorticity equation, there is no pressure because when you take the curl of the Navier-Stokes, curl of gradient, and pressure appears as grad P, so its curl is 0. So pressure is gone. So now you don't have to worry about all these challenges that come up with pressure in compressible flows. You don't even need to deal with that. You directly solve for vorticity, and you can use the vorticity, the stream function vorticity approach to solve for the flow and obtain velocity and vorticity there without the need to deal with pressure. So this is a common, popular approach, especially in 2D flows that you can consider instead of using the regular velocity pressure formulation. But we will not be talking about this in this course. Okay, so in next lecture, we will talk about the weak form derivation of Navier-Stokes and different approaches for solving Navier-Stokes with finite element.